So good morning, everybody. Thank you for joining. My name is Ryan Merrill. I'm the Managing Director and founder at Global Mangrove Trust. I've had the pleasure of working with a diverse community around the globe now for feels like 3 years, building the Grove system as a fintech platform for community-based mangrove funding and a series of management tools to support community-based regenerative forestry, including the Forestry Smart Ledger. So the technology that we'll be looking at this morning with two of our technical leads is the use of a remote sensing technology for space-based verification of forest growth. And what we're going to be looking at today is primarily the remote sensing components of the FSL. The FSL is a broader system that builds on these remote sensing tools to link them to a blockchain-based benefit sharing contract architecture to support regenerative forestry communities through the long term. But if you don't have a good, scalable, space-based impact verification, it's very challenging to build long-term financial structures to support communities. So we have begun our work at the remote sensing side of the challenge. And we've been blessed to get to work with some really, really wonderful volunteers from around the world, including Ankur's team in Hyderabad at the DBS Disruptors, and then a variety of other really talented academics, including Dominic, who's joining us ostensibly from UCSD, but actually from Ecuador today. So without further ado, because I think you guys actually know what GMT is doing, and a lot of our documentation is online for those of you who are watching this video remotely. I'd like to just turn it over to Ankur to share some additional background on the speakers today. And then as just general housekeeping, I'll make the effort to make sure that this recording is then hosted and provided not only to the invitees to the program today, but also to the broader global community. So thanks, that's all from me. I'm going on a mute. And Ankur, maybe we could invite you to give a little bit of additional background on the team.
Great, thanks Ryan. Good morning here from India. It's almost 6:30 a.m. here. So excuse us if my hair looks in different directions. I just woke up 10 minutes back. And if you guys know the problem which we have been working on, we have been collaborating with different members of our team from different parts of the world. We've been working specifically on biomass estimation and also making an attempt to predict the CO2 footprint being reduced by the biomass of different forests in different parts of the world. So basically, the research areas which we are focusing on, we have identified 4 areas. One of them happens to be in Mumbai, in Maharashtra region. There's a region called Van Shakti, which is very famous for the mangrove trees. But then we have also picked up a region in Singapore called Pula Upan. Then also taken up Myanmar and areas in Florida as well. So basically today we are going to showcase you 2 or 3 different approaches, and we have graduated from one approach to another, and we would want you to maybe appreciate the reason we moved from one approach to another, and show you the pros and cons of different approaches, and why do we think we are making that graduation from one technique to another. So we have Visa and Dominic who are a part of this amazing team. And by the way, I come from a bank in Asia, which is called Development Bank of Singapore. And we are all a bunch of data scientists. So Visa, whom she is going to speak today, she is a part of that data science team. And we have Dominic as well, who's all the way from US joining us, and he's a student. So maybe let me give you a little bit of background of both of them so you can appreciate the diversity in our team. So Visa is basically having more than 10 years of experience as a data scientist. She has done her PG in machine learning, artificial intelligence, has good amount of experience in natural language processing. And very recently, she has taken this taken this attempt to look at the geospatial space as well. And Dominic, he's basically a second-year student at UCSD. He just returned to the US to pursue his master's in international affairs degree at GPS. And he has recently had a focus on international development and environment policy. Prior to that, Dominic was also working in Accenture. He also comes from a fintech background. So we are basically a diverse set of individuals who have taken from the past 1 year, kind of made an attempt to solve this problem. So without really taking too much time, I'm going to pass it on to my good friend Visa, and then Dominic will take over. So Visa, over to you.
Thanks, Anku. Thanks for that. Hello, everyone. This is Visa. So I will just go through the first two approaches where we did a change detection between the two images to see the semantic change detection between the image over the time frame. And the next approach would be basically generating the features from our geospatial image and how we can fit into our ML. Okay, so we're going to the first approach. This is an article called Monitoring Mumbai Mangroves. So this article was published by NASA where they compared JPEG images between 2 years, which is 1988 and 2017. To find the difference between these two images, being a data scientist, I initially thought it would be a direct machine learning problem, image problem, where using neural networks, we would be able to see the segmented image and find the difference between these two images. And that's what we did over here. We used a faster RCNN technique and we labeled the land and the forest, and we were able to see the difference between the two time frame of same area of interest image. And how we did this, that is the method. The method is like we took the part of 1988 image, we masked them, that is we labeled them, and then we were able to train with the pre-trained model of VGG16, and we were able to predict the label, like we were able to segment it and classify, say this is the land and this is the forest. And there is a new development over here in this area, and there is a lack of forest over here. And we were able to match up with the article published by NASA. So considering this, we saw there is this need a lot of gap between the time frames. Say this is between 1988 and 2017. So we were able to find the exchange in the particular land area, wherein considering our FSL problem statement, we need to still look for lesser frequency. Say for a month, we need to find the difference between the images, so which we were not able to achieve through this approach. So we moved on to the actual luxury of using the geospatial images, where we took Sentinel as our input. Considering we took a lot of experiments between Sentinel, Landsat, and PlanetScope images, we took Sentinel image, which is of 10-meter resolution, which has a lot of features in it, wherein we say a geospatial image, it have multiple bands, it have it's not a simple RGB image, which is a JPEG image we used in our first approach, where here we have multiple bands. Each bands carry its own values. It carry NIR, which a human eye cannot detect the change, wherein a machine can able to see it. And also it have a shortwave infrared features, which is a part of a multispectral feature, which even helps us to go deep dive into the features, like more detail. Though it is of 10-meter resolution, we would be able to see much more details from the images. And with these bands, we also derived the vegetation indexes, water index, and these are the few indexes we consider, like NDVI, NDWI, NDBI, SAVI, which is a soil adjusted vegetation index. So these are the vegetation indexes we considered as the input features for our model. Also, we have looked into few of the features like biophysical features, which can be derived from our vegetation index. So this is all a mix of a package, which all we can derive it incrementally from the multispectral bands. And giving all this, so we would be able to segment our land, forest, water, and we will be able to predict it very clearly compared to our JPEG analysis. So going back over here, what we did, we collected all the features. So we inputted into multiple machine learning models. So to start with, we started with so this problem, again, I'm separating it into two problems, wherein one, it is a classification, which is a land classification, and the other one is the above ground biomass prediction. So it is a classification problem as well as it is a regression problem. So I'm splitting it into two problems over here. So considering the classification problem, we have done a random forest, we have done SVM, light GBM, and artificial neural network. For now, we have benchmarked with light GBM, because the reason is we are getting a high RMSE when we are going with a cart approach, which is again ensembling bagging technique. And also when we are going with the artificial neural network, we started with basic neural networks with a few hidden layers. And we were planning to increase our scope over in this particular area, as we have a lot of transfer learning techniques available, as well as we have our FastA approach in pipeline for testing the neural networks as well as the UNet. So we are currently working on it, but wherein we say the metrics also I would like to share. For the random forest, we got little high value of RMSE, wherein with light GBM we were able to achieve, this is for the classification, okay? Yeah, for the light GBM we were able to achieve a decent score, but there tend to be a lot of bias, that is there are overfitting between the models. If we see that the land area is less and the forest was more in that data set input, then it tend to be always predicting the forest area covered more, which tend to be overfitting, which we are still working on to fine tune that. And with a basic CNN architecture, we were able to achieve a 73% of accuracy. So yeah, this is our neural network where we took a same area of interest, because we don't know the ground truth for a different area of interest for both validating. We took the same area of interest, just we took a different time frame. So here we can see this is the actual ground truth image and this is the predicted image, and we got around 73 to 74% of accuracy. And with our light GBM classification, yeah, so we were able to achieve the classification accuracy of 93.4, but there is still a point of scope to be improved due to the overfitting, because the other classes were very less. So it's not completely accurate. So what we are aiming to do is, as we can reduce the number of classes in this, or the one more technique would be the ensembling technique, as we have built in the multiple models here. The one technique would be the advancement in neural network, where we can bring in more approaches like UNet, FCNN, and FastAI. Or we can also do an ensembling technique with our basic models, wherein in ensembling we will take an odd number of models and do a voting mechanism between all of the models to predict our land classification. So this is for a classification problem, wherein when to calculate the above ground biomass, this is purely a regression problem. So considering a regression problem, we don't have a manual human created biomass values for all the mangrove areas globally available. So we need to derive the above ground biomass using some allometric equations. As you know, the species of mangroves are globally different. It is different for different soil and different area, and based on the other features like temperature and ground soil nitrogen content, it varies. So we, without the human calculated measured value, to find the above ground mass is through equation, maybe with the derived values we can find it. So we don't have the hard code equation with us. So we would be asking this question towards the experts to help us to put this in place. Currently, what we are considering is we derive the n number of features from this sentinel image. Can we take a normalized sum or weighted sum of all these values to derive our above ground biomass and consider our regression technique? This will be one of the open question we have. Before I start, is it fine? So can I proceed with my questions?
Thanks, Vita. That was a lot. We probably can proceed, but maybe we'll just give the audience an opportunity to stay quiet or to interject a question or a point. If anyone does want to dive in, we'll give 30 seconds to the floor.
The one question I would ask is, have you thought about looking at using Google's AutoML, which will run multiple model types and allow you to identify which models are getting the best performance, or which data elements are driving the highest correlations?
Yeah. So we did this experiment initially with a couple of use cases in Google Earth Engine also. When we do using the code editor, we were able to do that. So we took the feature collection for the forest sample, the land cover sample from Google, and we did that using a couple of models similar to here, the random forest model and SVM. So, but we didn't try it outside. So we didn't try it on the Sentinel image, basically. We tried it on the Landsat images. But yeah, we can do that.
Thanks, Clinton. Let's keep our momentum. Visa, you're going to take us forward from here?
Yep. So I want, I mean, these are the two questions I have. And as a team, like we need some advice from the expertise in the group. So how to proceed forward with this. So as I stated earlier, for the biomass estimation, we are like looking forward to the different species. So currently, this is what our approach is. So sorry. So our approach, we generalize the equation. So if we can get a insight on that, like how we can put the biomass estimation equation in place to make our derived variable without a human intervention, without measured values, that would be so grateful. And also, as we don't have any measured values in place, so how we can benchmark it. These are the question which is related to a biomass estimation.
And we're going to be posting these questions in a Google survey online for those of you who are watching this recording after the presentation completes. So don't feel like you need to interject your responses here. Rather, we're going to be posting these and soliciting inputs and ideas from a broader community digitally over the next week. Thanks, Visa.
Thanks, Ryan. Thanks, everyone. So I would like to pass on to Dominic for discussing our approach number 3, where we are planning to combine the features derived from the Sentinel as well as the features where we can get it from LIDAR waveform details. So I will hand over to Dominic to take it over.
Thank you, Visa. Hi, everyone. So while Visa's team has been working on these different machine learning approaches, I've been researching some relatively new satellites that are using 3D type LIDAR to estimate canopy and potentially automate biomass estimates. So I'll speak to these new technologies, some of the research questions we had, and what we found out. And this is a quick introduction of how Sentinel and the GEDI features can communicate to be brought into our machine learning model. Next slide, please, Visa. Okay, so our first research question was, can the FSL automate biomass estimates by using GEDI open source waveform data? So to briefly introduce GEDI, it's the Global Ecosystem Dynamics Investigation. It's a high resolution laser ranging of Earth's forests and topography that's connected to the International Space Station. And it's the first spaceborne LIDAR specifically to study forest structure. So when paired with a GPS receiver, it can produce extremely accurate 3D measurements of Earth, similar to the one shown on the right of this photo. And there's 4 types of structure information that can be extracted from GEDI waveforms. These are surface topography, canopy height metrics, canopy cover metrics, and vertical structure metrics. And then with these metrics, you can estimate biomass. Next slide, please. Okay, so unfortunately, GEDI will not be able to automate the biomass estimates for the FSL, as it's a short-term mission. It will end in 2020 unless it's approved for extension until 2022. NASA confirmed it was never meant to be a long-term mission, but a global snapshot over a 1 to 2 year period. But when the mission completes, they will deliver a nice product of 500-meter gridded resolution, which will be more tailored for terrestrial forests, but will still have numerous mangrove areas. So at the least, this will provide a new baseline for mangroves when it was completed, and it will replace the current baseline of mangroves, which is from the year 2000. We have been having trouble finding Southeast Asia data from GEDI, but expect this is due to the region still being processed, as we're able to find data from Florida to test. And for canopy growth over time, it was recommended that we look more at ISAT-2. Next slide, please, Visa. Okay, so the next thing we looked at was, can the FSL automate biomass estimates by using ISAT-2 open source photon data? ISAT-2 is the ice cloud and land elevation satellite, which measures the height of Earth through laser pulses. It shoots 10,000 laser pulses a second. And it was launched before GEDI in September 2018. And it carries a photon counting altimeter that allows us to measure the elevation of ice sheets, glaciers, sea ice, and more. So although it was primarily for measuring changes in the cryosphere, it will also measure height across Earth's temperate and tropical regions and take stock of vegetation. Similar metrics as GEDI include canopy surface, canopy height, and canopy cover percentage. And then these can be used to predict biomass using algorithms such as GEDI's. And the photos here show the unique and slightly confusing way that ISAT-2 measures surfaces. So it's a different measurement track than how we traditionally see Landsat and Sentinel imagery. Next slide, please. So we have promising hopes for ISAT-2. It could potentially help automate our biomass estimates. It's a longer term option, but we foresee temporal and spatial gaps for our region of interests. So for example, the satellite sends loads of photons to Earth, and every 70 centimeters a photon returns back, but you don't necessarily know where it is. However, since so many photons are shot, you generally get a nice profile, but the resolution can range from 20 to 100 meters, depending on the number of returns of photons. So the trade-off to GEDI is that for the tropics, it doesn't pick up as many points, as it's primarily aimed at the poles. Therefore, towards the equator, the orbit is a bit further off. So we foresee some issues with repeat measurements in certain locations. However, NASA tested this in Florida, and it seems to be doing well for repeat measurements. And this photo here shows how the elevation profile of a forest can be shown from the returning photons over a trek. Next slide, please. Okay, so this brings us to our most recent machine learning research question. So can the FSL use ISAT-2 data as the dependent variable on our training model? So although GEDI and ISAT-2 won't be able to directly provide the FSL with biomass estimates for a reason. We can use the data to train our machine learning processes to more accurately predict canopy and thereby biomass, as alluded to in Visa's approach 3. And this photo here is an example of how the photons can be used to distinguish between water, mangrove forest, and a traditional forest, as well as the elevation profiles for each. Next slide, please. So the road to biomass and carbon estimators by using GEDI data as a robustness check. So differing from ISAT-2, the GEDI mission has formal requirements for generating data to enable the production of biomass maps, while ISAT-2 has no formal biomass requirement. So differing, GEDI has basically its own biomass algorithm built in that will be used after all the canopy data is collected. So in order to predict biomass in ISAT-2, one option would be to refit GEDI's biomass algorithm using the guidelines from a recent research paper, which is in our references, titled Biomass Estimation from Simulated GEDI and Other Satellites in Sonoma County, California. And this was from Duncanson this past April. And his results are shown in table 2 above. And they show that using GEDI night data produce the most accurate biomass estimates. And another option would be to use regional specific equations, so Southeast Asia in our case. And this was done from Simard and others research in 2018, which David, one of our coastal ecosystem experts at NASA, had used in his research. And they estimated biomass in Matang mangrove forest in Malaysia. And this is shown in the bottom table as well as their formulas. Next slide, please. So putting it all together, tentative methodology that could work for our third approach here would be to use Sentinel multispectral imagery to derive the texture, vegetation indices, and biophysical features as shown in Visa's approach 1 and 2. And then we could use ISAT-2 photon measurements to derive the canopy coverage and canopy height vertical features. This is specifically from their product ATL08. Then we would need to process ISAT-2 HD5 format into a KML format to merge with the Sentinel imagery. We found an example of this for full-real Python library, although that crashed my computer today when I tried with 37 gigabytes of photon data. We would then pick our region of interest and train the machine learning algorithm to predict biomass using Sentinel and ISAT-2 data. We could cross-check the predicted biomass with forthcoming GEDI biomass products and our other allometric HEB estimates. And then we would need to continue to train the model in the forthcoming mangrove baseline biomass estimates from GEDI as needed for accuracy. And this photo of Sonoma County on the right shows what one of these biomass estimate maps could look like. So our inputs would be Sentinel imagery features and ISAT-2 vertical imagery features. And then the outputs would be predicted mangrove growth change using canopy changes and biomass estimates. Next slide, please. So some questions related to this third process. So I've managed to obtain ISAT-2 data for our region of interest in Pulau Ubin, Singapore. The next challenge would be converting it into a geospatial format similar to Sentinel images, where it can then be used in our machine learning processes. So the overarching question would be, how can we best integrate GEDI and ISAT-2 training data into our current Sentinel image-based machine learning process? Specifically, we've been looking for algorithms to merge a vector of polygon features into a Sentinel image. And then also we have concerns if we combine Sentinel features and LIDAR features together, if the machine learning model will incline to overfit. So looking forward to everyone's thoughts on this. And there's a bit more further information in the appendix as well for those that are interested, as well as our references for all the research papers that were used.
Thank you, Dominic. At this point, we've kept to our time, so fantastic work, guys. I'd like to open it to just small roundtable, and just solicit some input from the group. If they've got some questions back on your questions or some initial thoughts, as Clinton did interject in the earlier stage of the presentation, this is a nice time for that. So maybe I can open this up to the floor.
I have a question, if I can pop in. Thanks for the presentations, very interesting, and really great to drill into some of the technical details of what you've been doing. With that in mind, I guess I have a broader question, because obviously I guess one of the aims of this is for it to be used to identify projects, etc. So my question is more applied, because there's a lot of uncertainty in some of the things that you mentioned around the differences in allometric equations, linking it to field measurements so that you can verify actually what your models are saying are reflective on the ground, and then some scale and resolution issues, like you mentioned. One of the I think the GEDI data set was 500 meter resolution, right? And some of the study sites like Ubin might only be a couple of pixels, right? So if all of those things create uncertainty. So for the users of this information, how much uncertainty are they willing to accept, especially if there are kind of things like carbon credits attached to some of these estimations, right? Then is uncertainty a big issue, or are the users of this information willing to accept a level of, a base level of uncertainty? Thank you.
Thanks, Dan. I may speak to that more quickly than some of the team. It's really a bit more of a market question. And I think for us, we are approaching this more from a scientific investigation rather than forward-looking towards that market application. Really, when we set out to engage this problem, we're vastly more interested in being able to provide a solution for communities as opposed to begin generating a substitute for the other verification systems on Earth. What's been interesting to see is the amount of appetite for advancements in remote sensing verification, not just from alternative markets, what we're trying to do maybe in Grove, but also from the teams at Pachama, at Vera, at Gold Standard, saying we recognize that this tech is advancing very quickly and our incumbent models are very labor intensive. So I'm not sure the degree to which that inflection of sort of acceptance of remote sensing based verification will be elastic to levels of uncertainty. I have no idea. But I do see a strong appetite for the information, for the knowledge, and for the toolboxes, the workbenches, to be set up and made available, which we're doing in an open source context, because the prevailing attitude that we're seeing back is that there's a lot of faith that this value proposition of scalable, high resolution, high speed verification is going to improve very quickly, much more quickly than the sort of analog models of using on the ground consultants. So whether or not that inflection of this technology being profoundly substitutable for human-based work is in 2 years or in 5 or in 7, that's the sort of time frame that people are anticipating, the speed with which the tech is going to be able to eclipse human-based work. And at the same time, the demand for scalable solutions is pronounced and only increasing very, very quickly. So I don't know how quickly the tolerance of the uncertainty or the level of uncertainty will merge and provide a sort of market valid product. I believe it could happen very quickly, very quickly. and mostly because I think the technology is advancing very fast. But on the other hand, I'd be super open to a countervailing opinion that says, you know, it could take 5-10 years before the tech is good enough to eclipse human work. That's all I got on that point, and I'm open to other opinions from the group.
Well, no, thanks for that. And I guess there's a sweet spot where both approaches combine in the most cost-effective manner. Thank you.
Yeah, I think one of the things, you know, when you start comparing resolutions of data sets, the biggest challenge really is if you say, okay, we need super accurate data and we're going to go with, you know, less than 1 meter resolution data sets. And then you're looking at hundreds of millions of square kilometers. And then the issue of having regular coverage for that broad area is very difficult. And then, you know, it's just the processing is very significant. Whereas you look at a low resolution platform and you get broad area coverage on a fairly regular basis, but then you don't have the detail. And I think the winning approach, from my perspective at least, is a combination of the two, where you have the broad area coverage and the low resolution platforms, which identify areas that require further investigation, and then you drill in deep with the high resolution data sets for those other areas. Because you just can't cover everything at less than 1 meter and be able to process it and have all the outputs in a timely manner. And it can be, you know, prohibitively expensive to do that. So, you know, we call it like a tip-off type scenario where you see a significant change that requires a further investigation, then you drill in on the high resolution, or you have a methodology where you do broad area, but then you have, say every, you know, 100 kilometers, a couple hundred kilometers, you then have a high resolution sample to then validate and see where you can get a better reading with the high resolution data sets. And then you have to apply some logic to then, you know, say, okay, well, we're seeing this density, you know, with the high resolution here, and we have a slightly different signal than we see over here with the low resolution data sets. Let's dig in there and then try and, you know, do some form of interpolation of the results in order to get a broad estimate. But, you know, it's interesting. I've had this conversation with Ryan in the past where some you know, applications, but they want to know exactly how many trees, the number of trees. And you're just not going to get that with even 10 meter data, right? Let alone 500 meter data. But there's value in that, in those other larger data sets that shouldn't be ignored. But then you could use the high resolution to fill in certain areas. That's another approach.
Thanks, Clinton. David Lagosamino has joined us from NASA Earth Observatory. David, how are you? Do you have any, would like to chime in on this or other topics you saw in the latter half of the presentation? I'm going to put you on the spot, but I am very glad you made it.
Sure, yes. I do apologize for being a bit late. But I think Clinton touched on some very important points there in terms of there is not one sensor that's going to fit everything, right? There are sensors that are good at specifically measuring structure, like GEDI and ISAT2 do, but they're measured in certain locations, right? And may not necessarily have repeat information, right? And then there's the more spectral stuff that has repeats, has a larger area coverage, but it's not giving you some of that structural information, right? So the idea is, I think here, you know, and some of the stuff that we've been working on is really kind of combining these, right, fusing these different sensors together to get some sense of what that structure and function looks like now, right? But then sort of keep training that model if, you know, if it's ISAT2 coverage, you know, and I see ISAT2 sort of being a longer term, it is planned for a longer term mission than GEDI. And so the idea is that you're bringing in new optical data, new ISAT2 data to kind of keep training that model, right, to make sure that you can then sort of extrapolate those structural characteristics. Yes, there's going to be some uncertainty, as Dan mentioned, when you start getting into different resolutions between what data you're bringing in, right? If it's ISAT2, you know, GEDI, the global product is aimed at 500-meter resolution, right? But if you're designing something for more of a local level, then the resolution can increase, because GEDI, the laser footprint itself is 20 meter on the ground. So it is representing a field plot in some sense. So again, the global model is going to be anywhere between 500 to 1,000 meters. But again, sort of more localized work on that and analysis, it can be, that resolution can be increased. And so again, it really is this sort of combination of multiple data sets that are bringing into this. And again, as long as there's some sort of uncertainty mapped with that, you know, field data is good, but we also know that, you know, there's a lot of studies coming out that, you know, field data is also, there's a high uncertainty in field data being collected when we compare that to terrestrial laser scans and those type of things. And so there's an inherent uncertainty in all of these measurements, but I think being able to show that uncertainty is sort of identifying where that uncertainty is, where we see higher uncertainty, where lower, that's where you can maybe put higher resolution data. Maybe that's commercial data sets, right, that you can look at, well, these are our higher uncertainty areas, let's focus on this, both with on the ground measurements, but maybe with some of the higher resolution, right, commercial, maybe it's drone data, something like that, that helps sort of inform those areas that from space we may not be doing that well.
Thanks, David. So I promised the group to get everybody out in 40 minutes. We are at 40 minutes, and this is what I'd like to propose. First, you know, we'll have the minutes of these conversations about uncertainty, data resolution, practical applications, and those are very useful. They'll be ongoing. At the same time, we're really eager to focus the technical community on the core research questions advanced in the presentation, as well as the tentative hypothesis, sort of the pathway forward that Dominic was detailing at the end of his presentation. So we're going to host probably all of these slides, or at least a focused subset of those, along with the recording online, in addition to a Google form with our questions and soliciting input from the community. So if you're watching this at home, or if you've joined us today, please let's keep this conversation running. We're very, very eager to have your contributions and your focused responses on our actual, our outstanding work problems, because we can't do this alone, and we're not doing it just for ourselves. So it's very much a collective effort. I'd like to say thank you to Visa, to Ankur, to Dominic. You guys are amazing. It's been such a privilege and an honor to work with you this summer, and Visa this spring. So with that, Ankur, would you like to say a word from your end, and then we can sign everybody off?
Yeah, I think great work. We are still on that journey of success. We know we may not have cracked all the pieces currently, but we are confident with the brain power we have, we will eventually reach there. But with your support, the intent is we should be able to reach there much more faster. So your support, your valuable inputs will definitely help us cross the race much more quickly. So pretty much that's that's what I want to say, Ryan. But thank you so much for arranging getting all the best minds from all over the world for this mini session. Thank you, everybody.
All right, we'll do it again soon. Dominic, Visa, Tomomi, Clinton, Barakala, Adrian, David, Dan, thank you so much for joining. We'll do this again very soon, and we'll put everything online for the broader group. Thank you all. Thanks, Dominic.
Thanks, everyone.
Thanks, everyone.
Bye-bye.
Bye-bye.
Thank you.
Cool.